While comfort work has people as its object, process air conditioning has things as its object. Process work seeks to condition air as necessary to make the production process more effective. Applications are found in the manufacturing of textiles, printing, electronics, and pharmaceuticals, where precise temperature, air cleanliness, and other conditions are critical. Textile manufacturing, for example, requires an atmosphere with relatively high moisture content, while multicolor printing demands constant temperature and humidity. Low-temperature work, or deep refrigeration, as it's sometimes called, uses mechanical refrigeration to cool and freeze a variety of materials for industrial and medical purposes. The temperatures produced are usually below 0 degrees Fahrenheit, and sometimes even go below -300 degrees Fahrenheit. Examples of its use include cryogenics, the study of low temperatures, environmental testing, space simulators, metallurgy, and gas liquefaction. We will not apply the basics of refrigeration presented in this series to process or low-temperature work. In order to understand the refrigeration process, it is necessary to understand heat. Heat is a form of energy which can exist on its own and can be moved about from one place to another. It is not matter existing as a solid, liquid, or gas, so it cannot be measured by weight or volume. It must be measured in a different way, which we will discuss in a moment. Heat can also come from other forms of energy. For example, appliances that use electricity generate some heat. This heat can build up in a space as a cooling load, which needs to be moved out of that space. 4 kinds of energy, light, electrical, chemical, and mechanical, can become heat, which we define as a cooling load. Sunlight and artificial lighting can be a large portion of the heat moving into a building. The electrical energy in light bulbs and fluorescent lighting ballast turns into heat. Transformers, electric motors, water coolers, and refrigerators also release heat. Some chemical reactions, as well as devices with a flame, release heat, thereby adding to the cooling load. Even people produce heat in varying degrees according to their activity, and numbers of people must be considered as an important part of the cooling load. When we think of heat, we tend to think of temperature, but temperature doesn't really measure heat content. To understand this, we need to look closely at matter, and in the discussion that follows, we will be referring to R22, a common refrigerant. In this example, we see that the smallest particle with all the qualities of R22 is a molecule. This is true of any substance, whether gas, liquid, or solid. The diagram shows several molecules of R22, first as a liquid at -20 degrees Fahrenheit. At this temperature, the molecules are vibrating at a certain speed or velocity. They are a certain distance apart, and they are arranged in a particular way. The density of a substance is a measure of how tightly packed its molecules are. It is measured in weight per unit of space or volume, for example, pounds per cubic foot. As the temperature of the liquid is increased from -20 degrees Fahrenheit to 40 degrees Fahrenheit by absorbing heat, the molecules vibrate more rapidly and move a little farther apart. The density of the liquid refrigerant has changed very little. Temperature indicates the average velocity of the molecules of a substance. Any pure substance is able to change its state. Solids can change to liquids, and liquids can change to vapor and back again. These changes of state occur under a specific combination of temperature and pressure conditions for each substance. The refrigerant R22 changes from a liquid to a vapor at 40 degrees Fahrenheit and a pressure of 69 psig, for example. Therefore, as we continue to heat the R22, it will eventually turn into a vapor or gas. Notice how much farther the molecules are separated as a 40-degree Fahrenheit gas than they were as a 40-degree Fahrenheit liquid. There has been a huge change in density during this latent heating process. The R22 molecules will be about 52 times farther apart as a gas than as a liquid, causing the density to decrease about 98% from what it was as a 40-degree Fahrenheit liquid. The change of state causes a big change in spacing and arrangement, but very little change in the velocity of the molecules. A great deal of heat is required to achieve this new spacing and arrangement of molecules, but it doesn't show up on the thermometer. This heat remains in the refrigerant as long as it remains a vapor. Temperature does not measure the spacing and arrangement of molecules within a substance. The heat that can be measured by temperature can be sensed by a thermometer and is called sensible heat. The heat that cannot be measured by temperature likewise cannot be sensed by a thermometer and is called latent heat. Latent heat is the amount of heat that is lost or absorbed into a substance, such as R22, in order to change state. The total heat contained in our sample of R22 gas at 40 degrees Fahrenheit is equal to its sensible heat plus its latent heat. This is true of any substance. Often the latent heat in a gas is greater than the sensible heat. For that reason, it is important in refrigeration that we measure total heat. This measurement is expressed in BTUs and will be discussed later in Module 2. Technically, anything above about minus 460 degrees Fahrenheit, absolute zero, contains some heat. Cold, therefore, is really a relative term. From a human viewpoint, ice feels cold to the touch because skin temperature is about 92 degrees Fahrenheit and the ice is 32 degrees Fahrenheit or below. The ice is only cold in comparison with a finger. Likewise, from the viewpoint of the outdoor unit on a central air conditioning system, 95-degree Fahrenheit air is relatively cool. The R22 refrigerant circulating through its tubes is about 120 degrees Fahrenheit, which is much warmer than the outdoor air. Since the goal in mechanical refrigeration is controlling the movement of heat, the right question to ask is, how much heat energy does it contain, rather than how cold is it? Temperature is the measure of the intensity of heat in a substance. It can also be thought of as the degree of heat of a substance. It does not measure the heat energy which was required to change the state of a substance from a solid into a liquid or from a liquid into a vapor. In other words, temperature measures sensible heat, but not latent heat. The two scales used in refrigeration service work for measuring temperature are the Fahrenheit scale and the centigrade scale. The boiling point for water at sea level is 212 degrees Fahrenheit or 100 degrees centigrade. Its freezing point is 32 degrees Fahrenheit or 0 degrees centigrade. A comfortable 75-degree Fahrenheit room is about 24 degrees centigrade. Since Fahrenheit is the most commonly used temperature scale in the USA, we will use it throughout this program. Heat transfer is also called heat exchange, heat flow, and heat flux. It is the movement of heat from one place to another, either within a substance or between substances. Since mechanical refrigeration is the movement of heat, heat transfer is the business of refrigeration service people. Earlier, we connected the idea of refrigeration with a central air conditioning system and a household refrigerator. Each of these required several steps of heat transfer to accomplish its purpose. Heat content is not the same thing as heat transfer. Heat content deals with how much heat energy is contained in a substance. Heat transfer, on the other hand, deals with how much heat is moved from one substance to another. Remember, when heat is transferred, the heat content of the source substance drops by the same amount that the heat content of the destination substance increases. Like all forms of energy, heat flows from a high energy level to a lower energy level. It might help to think of heat as flowing downhill, just like water. If the water level is the same for two ponds connected by a channel, there is no water flow between them. If one is higher than the other, water flows to the pond at the lower level. Similarly, heat will not flow without a temperature difference. Then it flows from a higher energy level, warmer, to a lower one, cooler. Just like water, the bigger the temperature difference, the faster it flows. We are committed to sharing knowledge and helping everyone improve their professional skills. If you enjoy this type of training, please like this video and subscribe to the channel. The next episode will be even more exciting, so don't miss it. You are also welcome to leave your comments or email us with the topics you are interested in. We will select the most requested topics and discuss them in future episodes.